Hello and welcome to the first time I'm talking about this. What would you like to cover today? Well, let's first. Here's some examples. We did some combined stress things. We were reviewing things we learned in mechanics and materials, but then we wanted to really dig into them and really own them, especially the combined stress stuff. So with a particular element. Also doing Mohr circle and increasing our knowledge of Mohr circle. To find the principal stresses, we went to the 3D version. And also doing 3D shaft problems. Was this a homework problem, this exact one? Dang, I hate it when that happens. Okay, similar. Similar is good, exact, not so good. With some pressure vessel stuff, curved beam stuff, contact stress, and then I did several others. But we can leave these because the solutions are already posted and these problems. So we could pick something else. Unfortunately, there's not a whole lot to choose from the book, but we can go problems in the book. We can also, you see the big binder and stuff? That's just problems that I've written since I've been here at UHart. But anyway, we can try to go through the big binder, or I could invent one. It's dangerous. A lot of hazards right there. All right, so somebody speak up, say something. By the way, I won't be doing any strain transformations. Have no fear. There's no strain transformation. That was just for your edification. Edification's a great word. I like that. But anyway. So anyone speak up and forever hold your peace, or keep talking.
Could you do an example of 3D Mohr circle?
Yes, absolutely. It's a great, great request. I can absolutely do that. Here's a picture of the wall. But instead, let's go here. Here's my document, Karen. Wee-hee. We'll bring Yeti, follow me. You don't want to slam it down. I'm going to be a podcaster. I'm going to have my own podcast. This is a podcast. This whole thing right here, a podcast. Let's just pick one out of the book so I don't have to use my imagination at all. I should have like a screen right in front of me. Sorry. We will adjust. I'm going to go on mic. I just think louder's better. There you go. So if you were to go into the book and look for this, it's going to be, where are you at? Where are you at? This way. There you go. There's sections. There's a bunch of problems right there. There's a couple, I recall there's a mean one. Dr. Ghosh, he actually pointed this out. He goes, well, here's one that I really like because it really messes with the students because they didn't bother to look. I'm going to try to find it. It would be mean. I wouldn't do it. Apparently he would, though. I'm looking for one where it's out of plane, but you didn't quite notice that it was out of plane. Oh, there it goes. X and Z and XY right there. See, it was mean. You wouldn't really look at it and notice that it was not in the same plane. That is a challenging one, but let's not do that one because it may be confusing. It would have to, it requires some explanation, and it really, what he was pointing out was it really is a test to see, do you really know it, or have you just memorized this kind of like routine? We would prefer the former, but it's not so bad to just do the second, or latter, former, latter, whatever. So let's go ahead and try. Yeah, this is a good one. Okay, A. So 3, I like for posterity to keep my notes. And we go to this one, A. And what we're going to have, this is not a bad thing to practice, is getting your mind set on what the element needs to look like. You see we have a -80, a -30, and 20, but it's clockwise. Okay, so this is a tau xy. So in the x direction, we're going to have 80 megapascals, and in the y direction, right? So apparently this is the xy. That's good to know. We're going to have 30 megapascals. And then for here, we're going to say this is clockwise. Okay, well, which one do you mean? Okay, so remember that X and Y, that's face and direction. And so the face and direction, that would mean this face and up and down, right? So this is the face and up and down in the Y direction, and they're saying this is clockwise. Therefore, that's that way right there. Does that make sense? That logic? Walking through that logic, okay. And then, of course, once you know one direction of the shear, you want to have the arrows facing each other. That's going to prevent the rotation. And then they need to be going the opposite direction on the other side. That prevents translation because the thing needs to be in equilibrium. So that's the logic that goes with the arrows. All right, just making sure because there's a couple points right there, right, to get that messed up. In terms of the understanding, oh yeah, and the value was 20, and I usually put it right here up in the corner. I kind of got them close to each other, but whatever. All right. How we doing with our focus on that? We're pretty okay. Speaking of focus, he tries to focus. I'm not gonna really do it to scale. I don't really care about it being to scale, but quasi to scale. I mean, it isn't imperative that it's to scale. One thing the next thing to say, when I ask you to do it and draw it, I don't mean for you to do the graphical estimation of the thing. I just want it to scale so that you're thinking the thing through. So when I say to scale or approximately to scale, this would be good enough. Without graph paper, you could do it to approximately to scale. That's what I mean by that. So first, we notice that they're both in compression. And this one is about 1/2. I know it's not exactly 1/2, but 40, close enough, right? So if you were just to do this right here, and you were to do it to scale with your ruler right here, this is a little more than twice that one. So maybe that's over here, that 80. Or it would be, I shouldn't put that dot right there. I should put maybe just to make a little tick. A little tick. Should reserve the dot for the actual face when we get over here. But it's in compression. And then maybe if we were to pick right there, like we'll say this right here is 40, so that would be 60. Is that right? 40, 60, so this would be like 1/2. Here's a 20. So maybe like somewhere over here might be 0. Is that okay? All right. And then, so like I'll make a little 80 and just little tiny numbers. This is just for my own benefit. You don't necessarily have to do this, but it wouldn't hurt you to do it. I kind of think it's not terrible. It's not great. It's not terrible. So then we're going to go 20. So first off, I'm going to go this face. And he's going downwards clockwise. And one way to remember the sign conventions is to draw this thing up. And by the way, I'm not sure. I might have made this too close to the top of the page. So we'll see if I burned myself that way. But you could think of the sign conventions when it comes to the shear as being, you know, we know it's clockwise for some reason it's positive. Doesn't make any sense, but that's the way the book says to do it, so we'll go with that. The rest of the world, clockwise is negative, but that's right. Here's about 20 right here. I want to make it about the same thing. We could use our ruler if we wanted to, and go, oh, there's 20 right there. And I actually didn't do that bad of a job of making that 20. But we're going to come over here for this face, negative 80 and 20, so somewhere like right there. So there's actually our spot. I'm going to make a dot right there. And I'll go, I started writing 18. Get a grip, dude. Okay, cool. Don't talk to yourself in front of people. All right, I won't. Right here, so we say, okay, so here's another, here's the negative 20, so we maybe, I'll make a little light line right here. On the face right here, this top face, I don't know why I made that mark right there. That was a stupid mark to make. It should be somewhere in between here, right? This is our 30. So down here is where our other point is. That would be our negative 30 and a negative 20. That might, writing that might get in the way of my other circle, but I don't mind that so much. It occurs to me I should say something. I would recommend for those listening at home and those here, try to push for you to start using pencils. Well, not with regard to tablets, that's fine. But so many people take tests in pens, and it just sometimes it's just an awful mess, an atrocity. It's just a tragedy. And well, I just like doing it that way. Well, okay, that's great. Well, then stop liking doing it that way, or just do something you don't like anyway. But anyway, in the midst of doing this kind of thing, it's often necessary to acknowledge a mistake that gets made and try again. You don't have to have a compass, but I think it's a wise thing, especially if you can get one that works correctly. Oh, I never know which one to use. Should I use this pen? Actually, he looks like he kind of no, he's still kind of there. It looks like it got pushed in. I'm going to go with that side then. There's a little tiny point in there. And it wouldn't hurt to sharpen that up some, but he's not sticking out very far. I used to have, oh, you know what I have? Oh man. Okay, so tragic story. My father-in-law passed away. He was like last year. He was a great man. He was also an engineer. We had a lot of great stories, but I have his kit that he had from college of his compass set. Really nice set. Go find yourself a really nice set. It's a nice thing. They don't exist quite as much anymore. I guess there's not as much call for having a compass set. Chances are, ooh, that got pretty close. I'm like all impressed with myself because even on graph paper, I often don't get very close. But here you go. Here is our main. Here is the first Morse circle that we're going to do. We could finish the Morse circles now because one of them. All right. So here's going to be where the principal stress 3 is going to be. All right. And here's where principal stress 2 is going to be. And right here is principal stress 1. How do I know that? When it's 2D, all of them, always one of them has to be 0, right? So Kyle says exactly right. Just in the nick of time, Kyle comes in, all wet, invest in an umbrella. That would be what the electrical engineers would pick on each other, would pick on the mechanicals to say, what's an umbrella and a stapler have in common? It's like, there's only 2 things a mechanical can design without having an electrical engineer involved. That's what they would say. So there you go. There's a reason to buy an umbrella. Especially a really well-engineered umbrella, because they have these special ones now that won't go inside out. And look at how terrible I did on that. I did a little guesswork, and I'm going to. Here's my redo. Oh, it's not doing great. Okay. We could go ahead and put that one in there if we wanted to. Well, we could actually start throwing some numbers in here first. Maybe let's do some numbers and we'll finish this off in a second. So the first number I would pick out was the center, C. And that's just going to be sigma x plus sigma y over 2. So for us, that's going to be a negative 80 plus a negative 30 over 2. Oh, I didn't bring my favorite calculator. To use my phone version of it, but my phone is like I say nearly dead. That's not nearly as bad as my daughter is like at 1% like all the time. She lives on 1%. I can't do that, man. Just can't do it. But you see, here's even I have my HP reverse Polish notation calculator. Trying to get. I'm going to recruit one of you one of these days to get you to change that RPM. Professor Al Chubb, she convinced me to become an RPM person and set me on this path. Okay, so we have a center. Now here's the radius of this. You can follow the formula or look at the formula, refer to it in the book. I just prefer to look at this. You know, this is actually, to me, this is one of the purposes of drawing the thing is to recognize, okay, which, and I'm not going to, this one, because it doesn't straddle this line, either one of these would have worked pretty well. But I'm just going to go and look at this and say, okay, what is the leg? The leg is going to be the center, 55. Somehow I managed to write an 80 in a terrible spot. Here's my 80. Should have been right there. Right, that should have been the location of the thing. The 80. I don't know why it showed up over there. But so I'm going to take 80 minus 55. Does that make sense? To get this leg? Because this is where 80 is. And it doesn't matter positive, negative. I just want this length. So I go 80 minus 55. And that'll get me that length. And then all I need is this leg right here, which should be 20. And boy, do I wish I could get that thing right there to go away. I wonder if that shows up on the video right there, that little thing. It's because of this Yeti. I actually had to get a program that turned that off. I had to search and find a program that turned that thing off. It's kind of stupid. So A minus and square it, and then I should know what 20 squared is. Oh yeah, that would be 400, right? Duh. Plus square root. So if I did the numbers right, I get 32.0, call it 2. And now I can find my, let's call it A to start with. Sigma A is 6 plus R. 6 plus R, C. Why did I call that 6? C plus R. So C is negative 55 plus 32.05. All right, so that's going to be 55. So negative 22.98. That's weird. I think it's right though. But, oh, 2. There you go. I don't know where that 5 came from. Oh, is that how it's going to be today? Apparently. Okay. Then you go sigma B, C minus R. Okay, so you have a negative 55 minus 32.02. You should be able to do that in your head. That's going to be a negative 87.02. So based on that, this is going to be sigma 2. And this is going to be sigma 3, right? So there you go. This is, as we mentioned, that's sigma 3. It's the lowest principal stress. This is sigma 2 right here, which I put in a bad spot. And then sigma 1 is going to be equal to 0. And now a very important thing to do is to find the shear stress, absolute maximum shear. So the abs max is always going to be sigma 1 minus sigma 3 divided by 2. Always. So that's going to be 0 minus 87.02 divided by 2. So sigma abs max is 87.02. Could do it in my head, maybe. No, probably couldn't. 43.51 megapascals. And if we're looking at the big picture here, let's see. Boom. Let me get that. I'll zoom out. Zoom out. There you go. Looking at the big picture here, that's going to be somewhere over here, guessing, and will be nope, terrible job. All right, so I'm going to do my best approximation here, something like that. All right, so that was not supposed to overlap here. Let's pretend it never happened. Here you go. You could also use the ruler as a eraser shield. There you go. And then so right above this, which would hope that would be 43, but it's not. This is the tau abs max. That should be 1/2 of the way through here is where that's going to be, and it'll be right up to there and right up to there. Is that clear? Did that solidify anything during the process?
Where did you get the positive 80 in the R?
Positive. No, I didn't. Okay, I just ignored what the signs were right here. I just knew that this was 80 and that's 55. So because it was squared, I didn't care about the signs.
So it's supposed to be the first one minus the second one, but since they were both negative, it just...
Well, yeah. I was just looking for the length. I was just that was my mindset. Was I'm just looking for this length, and I'm not caring about the the positives and negatives. I probably should, but I did not. Any questions about this or mindset or anything? Did that organize it? Did it clear up some things? Okay. Best thing to do, run through some yourself, right? Even if I feel comfortable with that. You don't until you do it, right? And then you'll make sure. I can't emphasize it enough. It is just the way everyone's brain works, right? And then as soon as you're on a test, you have that extra pressure. And where you had something organized because you had passively seen it. But now when you actively have to do it, it's different on an exam. And so many students over the years have said, but I understood everything, and then I got to the exam and it just all fell apart. So just keep that in mind. All right, great. Another kind of problem.
Can we do a curved beam?
Yes. I might have to invent one. So dangerous. No, don't. Sorry. About the only two kinds of curved beams I would ever do would be a rectangular / square or a circle cross section. The rest are just too time consuming. It would be unfair on one level. Let's do a square one. Square. I'm scared though. I have fear. I'm going to in a panic look through the book here and try to find what's available to me and hope. See, this one's too hard. This is too hard. Ooh, maybe no. They said this is an oval. Maybe we could pretend this one. Let's pretend this one is a square. We won't have access to the right answer. Well, you're not seeing what I'm pointing at, so that doesn't help any. This strut right here. This little strut, because this is sort of like a real practical thing, because a lot of times when you're putting a machine together, you go, oh crap, this linkage is going to get away of this other part. So they're like, I know what I'll do. I'll just make a, you could say like in an FSAE car, I bet these two things are occupying the same space. One of them must move. It's not out of the realm of possibilities. All right, so we're going to pretend that is not a oval, which is elliptical, which is kind of evil on one level, because I don't even know if we have an elliptical in the. I think you had to that's not my recollection, is that we didn't have an elliptical as one of our types. I'm going to stop complaining about myself at one of these days, but I am going to complain. Today is not that day. I keep forgetting to tab this book, trying to find this. So am I wrong? Do they have an elliptical? See, they don't even have an elliptical here. There's no elliptical here, but I guess you could kind of guesstimate what the circle is. But we're going to make the thing a rectangle. So let's go back and read the problem and write down the problem. How are we doing? Not really great. All right. So I'm gonna have. So this is what 145 but we're gonna make it. We're gonna adjust it. Oh, that was not a grid. Oh, I'm not liking my drawing. That was weak. Weak. Should use a straight edge. I should be a good role model. Yeah, I don't know if that's any better. I don't feel as bad about it. So let's see. We say that right there is going to be. Ooh, let's see. Gonna get in the way. All right, and this distance apparently is 9 inches. And this, I'll move it over here, this is 12 inches radius, they said. And other things we said. The offset tensile link, all right, so it's in tension, which they should with the arrows. Is shaped to clear an obstruction with a geometry, as shown in the figure. The cross-section at the critical location is elliptical. Jerks. With a major axis of 3 inches and a minor. Okay, so we're going to make it this way right here. So this is going to be 3 inches by 1.5 inches this way. And the load is 20 kip. I do not like kips. 20,000 pounds. 1,000 pounds. And we want to estimate the inner and outer stresses. All right. That's not a terrible problem to have to do. The elliptical one is that's just mean. We could probably estimate it though somehow. But let's go through the main process here. So once again, tab your book, dude. I think we're 318 is the section for this. There you go, 318. So our main thing, we want to start to get the variables that are going to be that are necessary for us. RO and RI are important ones, right? And that's all. Those are the radius to the center of curvature, which they've provided right in there onto the thing. So this is RI is what they told us was 9 inches. All right, so RO is going to be that 9 inches plus the thickness. So 9 plus 1.5, which is 10.5. Did I get that right? No. Yes. Sad that I can't remember. Tori? No, don't be sorry. I want to hear questions. If you have a question, you could just say it out loud. Or you could try to figure it out yourself. I don't mind.
Wait, is it RI to the inside, but then isn't the 9 inches we're given to the step?
You know what? You're 100% right. My bad. Thank you, Tori. I was what? No, I don't need to. I was not thinking. 12. You're right, Tori. Thank you. See, I need that kind of help because that's the kind of day this is going to be. It's a rainy day. So blame it on the rain. That's a song by Milli Vanilli. You guys familiar with this? One of the greatest. They were complete frauds. Other people sang their music for them. They had these two guys that were dancing around and singing, and they went to the top of the charts, and then it turns out they could not sing at all, and there was totally studio musicians doing it. But blame it on the rain was the name of the song. You don't care. Right. Milli Vanilli. We covered Milli Vanilli. That's good. We weren't going to do this today, but we did. Yeah. Always. We're going to starting now. We're going to get back on track. Okay, so other things we need, we got RI, we need H. H is just going to be 1.5. Looks like we have everything right there that we need. We do want to get, let's just go ahead and write it down then. RC. We could actually just think this ourselves, or we could write this out. So R, this is going to be 12 plus 1.5 over 2. Can I do that in my head? No. So that'd be 0.75, so that'd be 12.75? All right, thank you. As long as you say I'm right, I will trust you, but I will not trust my own noggin. Nope. Trust issues. Can't even trust yourself. I don't trust Milli Vanilli. They got busted at an MTV performance where the tape or the CD, I think they were doing a CD and it skipped. And they had to run off the stage.
Is the RO plus or minus?
Should be plus.
So then it's 13.5 out of 25.
Wow.
Up at the top line.
Sorry. I'm depending on you. You must get me through this Milli Vanilli thing I got going on. I really want to play it. That's what I got impulse control issues. I really, really want to play it, but we're not going to play it. I'm counting on you to look it up afterwards. Behind the music. The rise and fall of Milli Vanilli. RO 13.5. And then RI 12. So let's go 1.5, we'll put it in the stack of 13.5 and divide by 12 and take the natural log, naturally. He thinks he's funny, he's not. How many more sig figs do I want? 5, 3. Yeah, you get another sig fig. 2/8. You can't have too many at this stage right here because we're about to subtract something. That's this where we end up with problems, right? So we got E is equal to RC, and that should have been 12. My bad. So yeah. Okay, you can do this. And this is always going to be bigger than this one. But look how small this is. Look at the difference, right? So you can see why I wanted to go so many sig figs. Does that make sense? Because you're going to go 12.75, and you're going to subtract out 12.73528. And you're going to get 0.01472. That's enough. Four is enough. Once you get to that level right there, you should be okay, generally speaking. I mean, you could give it another one. You could give it a lot more if you want. It doesn't really matter. It's only my big sig fig thing, aside from this, don't round off too much in the middle, but use as many sig figs as you want while calculating things. That's totally fine. It's at the end. Don't give me more than 4 sig figs as an answer. It's just, we just don't know, we just don't have that much certainty. And so it's a communication thing, but it's also just a reminder. It's like a mentoring thing, just to keep in mind this healthy suspicion of the values that we use. All right, so we also going to need, so here's the main equations we're going to use. We have to remember, though, we are in tension, we are in axial and bending at the same time. And in this case, we're going to be tension and bending at the same time. So we need to find the area as well. So we'll find, so this is all the geometry stage, by the way, in a problem. We want to try to cover the geometry. And this is not so hard, right? 3 times 1.5 Is that 4.5? I trust you, but I went and put it in my calculator anyway. Okay, and lastly, we need the moment. All right, so that was all geometry. The next is going to be loads, and that's a common thing when we're doing a problem. We do the geometry, some geometric things that, you know, sometimes we're there just to get it out of the way, but also it's just, hey, we want to take stock, and then we will go to the loads. So in order to get the loads, to double check them, we need a free body diagram. And we have a force right here, and that force is going to go right here. There's a reaction force in the x direction. But because there's an offset, we're going to take the moment about this reaction. And that reaction is going to happen at the centroid. Right? It doesn't care about the neutral axis. It doesn't know anything about the locally. It doesn't realize it's a curved beam when it comes to the where the center, and that's going to be location. But that's easy enough. So what we're going to find right here, if I did this, I'm thinking. Okay, so yes, here you go. This is where the 9 comes into play. It's going to be 12 minus 9. Everybody okay with that? All right. Which is 3. Yay. Yay for me, remembering things. All right, and so because we're taking the moments about this, that's going to be counterclockwise. So the moment here is going to be clockwise. That's a reaction moment. So we can go the sum of the moments, and we could call this point, I don't know, call it A, because nobody used it yet. I don't think. And through this right here, we're going to have a negative m, and it's going to be plus this here, force times, oh, I wish I gave this right here. Wish I gave it a symbol. Yeah, I'll just use numbers because I don't have a thing on here. So this is going to be the 20,000. And it's going to be the tray. So I think the moment is going to be 60,000 inch-pounds. I think we're done with the loads portion of this. If we're going to be like really sticklers, we could also do sum of the forces in the x direction equals 0. Excuse me, that was gross. And we go negative 20,000 plus Rx equals 0. But obviously, we knew what that was going to be. But it's some reflection on what we're doing so that we're not just blindly going through these motions, is to note that this is going to cause compression on the outside. Right there, right? That moment. A lot of times it's easier for us to use the stump to kind of like visualize which load is going to cause what kind of stress. But you can look at the free body diagram. It's just kind of easier to think of. It's a lot of times about the stump. But you could just look at this load right here. This reaction load causes tension here, it causes compression here. And this guy right here is causing tension across the whole thing in terms of the axis. So the combined stress aspect of it. So we can go to the stress side. And the equations that we will write down is, so for the inner, it's going to be F over A, which we got to remember that that's not included here. They didn't write it down anywhere as an equation in the book, but it is in the example that's right after the thing. And then that's going to be plus, because we could tell that situation. And so if I were going to ever ask a question like this, I probably would reverse this stress, this direction right here, just so you to measure if you really understand what's going on, or if you're just blindly mimicking what's in the example. Because I want to see if you understand the thing, if it really is sinking in, or if you're just gonna, I will do what you tell me to do, kind of marching orders kind of thing. A thinker versus a plugger and trigger. Oh, more geometry I should have done. I forgot about the CIs and the COs. So let me breathe. Let me take a little step back. And sometimes it takes a little bit of I don't know, maybe a diagram might help right here. Let's take a look at the diagram. Right here is our diagram right here. Here is our center. But I should have made a, here's our centroid. They're going to be too close to each other. I don't know if what I'm doing right here is worthful. But here's going to be our CI, and here's our CO. And good place for it, I guess, over to here. CI is going to be our, let's see, and this right here, trying to, what do we call that sometimes? Just R? Okay, we want to go RI. Yeah, there you go. It wasn't thinking. That's going to be our RN minus our RI. Did I get that right? Because we want the distance, like one of these needs to be the, to the RN, needs to be the neutral axis. So we want to get the distance that's right in there from here to here. So maybe I should have drawn it right to there. So if we did that, we're going to get 12.7353 minus our RI, which is 12. So we could do that in our heads. 0.7353 inches. And I got 4 sig figs. Good. CO is now going to be RO minus RN. It's going to be this one right here, right? So that is, we got that wrong a couple times, 13.5. I said we, by which I meant me. And so we go 13.5 and 12.7353, 7353 minus, and we get 0.7647 inches. Made noise for some reason. Now we go F over A, 20,000 divided by 4.5 plus M, 60,000, CI, 0.7353 divided by 4.5. E, EB number. And it's a denominator, so I guess maybe, I don't know mathematically if it has any truth to it, but it feels like it has more of an influence when it's the denominator. You can blow the thing up because it's small. It's a small value. RI is 12. All right, so in between numbers, I think it's always a good idea to go in between numbers. Doesn't hurt anything. So you have 4,444. I like that. PSI. I didn't turn it into KSI yet. And then this guy, and this is helpful because we're going to do it again, and we don't have to calculate it again. So we save ourselves an itty bitty amount of time, just a little tiny minute. Going to go 60,000 times 0.7353 and divide by 4.5 and divide by our E of 0.01472 and then divide by 12. Boom. And we get 55,503. So sigma I is going to be those two things together, which is 59.95. And now I'll turn it to KSI. And we put a tension. And then we can go to sigma 0. It's going to be F over A, not 0, O for outside. Not equal, sorry, minus, because this is going to be compression on the outside. So you're going to have M, let's take a look at the equation. You'll notice that it's negative right here onto the thing. If you could see that, I don't know how, could be a little bit better focus. CO, and go A-E-R-O. And we don't even need to write this anymore. We just go 4,444 minus 60,000. CO is up, whoops, out of range, up there. 0.7647 and divided by 4.5. And E, where'd you go, E? Right here. 0.1472, and RO, which we found to be 13.5. Thank you. That was a terrible brace. I'm gonna make a perfect brace. Nope, still not great. And 60,000 times 0.7647. Is that right? Yeah, I think so. Divided by 4.5. Divided by 0.01474. 72. And 13.5. And we get 51,000, that's negative, we'll remind ourselves, 308. So the outside is going to be, see, I'm 4, and I just remember that it's minus. So I get 46.86 KSI compression. How do you feel about that?
So are we not looking for it on the, like, so the pipe's like this, not on the outside of the pipe, but the inside of the pipe? Because wouldn't it be tension on the bottom since the pipe being pulled on the outside, not pushed in?
Okay, so you could think of this as, no, it's going to be compression on the outside because we're pulling on this and it's trying to make the thing straight. And in the process of trying to make it straight, it compresses that side. Even though it's still pulling it a little bit axially, it's trying to make it straight. And in order to make it straight, this has to stretch and this has to squish. It's a great question. It does. It's only when you start to pick it apart, piece by piece, that you can be convinced that your gut will tell you some things, and but then you gotta retrain your gut to what it tells you, because that gut can tell you the wrong things, especially if you ate like a bad burrito. It'll tell you a few things. You don't want to listen to your gut. Sometimes it's going to tell you. Never mind. I won't go there any further. How about we're taking requests? We're taking requests. Milli Vanilli, more Milli Vanilli content. Gave them way more cred. My roommate, Christopher May. That was only for a brief part in sophomore year because I went between roommates, a couple different roommates. I guess I wasn't easy to get along with. I don't know. He would listen to Milli Vanilli, but he was this huge dude with a very, very mousy voice. Ted, say, big dude. Listen, I'm listening to Milli Vanilli. Shut up. Okay. Huge dude. He'd watch TV all the time. We weren't allowed to. He had a secret TV in the room. I don't know how they can't regulate. They must not allowed to have phones. They must take their phones away. No, I don't know. School's going downhill. It's going to hell. Mercer Marine Academy, I mean. It was weird. I'm going to start telling stories so you don't ask me a question.
What are the possible topics?
You know, that was the nice way to say what's going to be on the exam. Oh, that's a great idea. Okay, well, mostly what we've seen in the homework, right? You know, those big topics. You know, the first couple classes were basically statics review, right? So like we had statics type of review. Then we had mechanics of materials basics review. Then we did like combined stress, but you know, and that was combined stress / Moore circle, if I remember, part 1. And then we did pressure vessels. Am I telling the truth here? Is that your recollection here? And 3D Moore circle, which was part 2 of Moore circle. And I can't remember. 5 was 5. So this was homework 1. This was homework 2. Homework 3 was, let's see, 5 and 6. So you know what's a better way to do this is to go to here. I wonder if it's kicked me off of here yet. No, I'm still here. So let's take a look. My recollection. By the way, I like the little have like little pictures there. What I need to add on to there is learning outcomes. I did that in it's on my list of things to do. It's been learning outcomes. But anyway, here's theory. It was more circle principal stresses, and then more complicated shafts and things like that. And then we did pressure vessels and 3D Moore circles. And like you said, I think it was more pressure vessels. And more pressure vessels and combined stress things. We didn't really cover any of this stuff. I think I briefly talked about rotating rings and press fits and thermal expansion, but we're not covering any of that. And then there's 6 with strain gauges. Yes, we're not doing strain transformation, but we could have. Probably not. I just never feel like there's enough time on an exam to be able to cover some of these things, so I'm just not gonna. Usually, I could ask 3 to 4 questions. Sometimes the 3 questions would only be because I combined something into one of the questions and merged them into the thing. But I'm usually looking for certain skill sets. I'm trying to measure certain levels of mastery or of recognition of aspects. Whether we have the curved beams as 7, and then I think 8 was contact stress. With a little, I don't think I'm going to be asking any contact stress. If I did, it would actually be probably on the final exam, just because I was feeling like a jerk. But I want you, because it would be what I would be measuring is your ability to relearn something, which is a really important skill set, because you will forget everything that you don't use. It's just a fact. But have you developed your ability to use Shigley in such a way that if somebody were to ask you something that you don't immediately recall, you don't have the thing that you can mimic, that you could look through the thing and go, oh yeah, I remember that and this, and I'm able to pick that up, right? So this is my mindset, the thing as an educator, my priorities, that I'm not trying to trick you by doing that, but it does seem like a dirtbag trick. But I am trying to say, have you developed in what I find as the priorities that I want you to be able to do? So you don't really have to spend a lot of time on contact stress here. I'm telephoning that out. So yeah, it's really sort of like curve beam. I think I just used up the curve beam problem I would have asked. But if I did ask one, that would be like about the level of the thing. But it's a time-consuming problem. That's one of the aspects that everybody runs out of time. So in your work, I would suggest that you mind your time, right? You do a problem, get it all straightened out, do another problem, and see how fast you can do it. See where you can not skip steps, where you can economize. That's a better way of saying it. Economize your approach to the thing. The number one problem I find, and I don't know if I'm too far away for people to hear, the number one thing I think is a time waster is not moving your pen, don't use pens, pencil, just to sit and stare at a problem. It's not going to go poof and come to you. It's more likely, if you don't know what you don't quite know how to solve it, it's probably going to come to you while you're working through the things you do know, the things that you can do, right? And so that blank piece of paper, that blank problem, it just drives me nuts. When someone turns in a problem and there's nothing there. The only upside is it's easy to grade. That's the only upside, but I will take that hit to see you demonstrating, hey, what do you got? What do you got on this problem? What can you, show me something. Show me what you got, right? So if you're moving your pencil, you got a better chance of going, oh, I got it. That's what I'm trying to measure. That's the holy grail of a problem for me is one in which I pull that out, right? That I'm like, oh, ha, ha, ha. And they struggle, they overcome the struggle. But that's a dangerous thing to try to write a problem like that, because you could get it so that doesn't happen, right? So they've got to find that balance. All right, so that's what's going to be on the exam. But you can almost count on, and I meant to write this down. Let's put the camera back on. Here you go. What's going to be on here? Door handle. Pressure vessel. Principal stress. Principal, just like you had, I went to the principal in second grade 17 times. His name is Dr. Eustock at Alexander Elementary in Alexander, New York, and he told me if he saw me again, I was getting kicked out of school forever.
The 17th time or the 16th time?
Was that?
Which time did he tell you that?
I think it's probably the 17th time. I just remember 17. It just sticks in my head. I have a small recollection of this. I do recall sitting outside his office crying many, many times. And then lastly, shaft problem. I won't say it's a 3D shaft problem. If it was a 3D shaft problem, I could do a 3D shaft problem, but it would take too long. So a shaft problem in requiring shear moment diagram and probably some type of torsional diagram and torsion. By torsion diagram, I mean I want to see this thing right here. Find the torque. or a torque balance, or something along those lines, where you have to do an FBD down the length of the shaft and looking at that thing and finding torque. It's one of my priorities. So we could do, in our practice here, we have 54 minutes at least. We can go over, I don't care, but just looking at the clock, because I can see it right there at the bottom. Here's your menu. Here's your menu. We'll write menu down. We could also go more milli vanilli. I can't remember how, was it milli vanilli?
Can we do a pressure vessel?
Yes. We can do mean things to pressure vessels too. Be cruel and unusual things to pressure vessels. So let's talk about something that would like make it 3 problems instead of 4 problems. And a lot of times it might involve a pressure vessel. Let's think up something. Oh. I'm gonna watch him try to pick this up. It's fun to watch me pick this up. Oh, I got it. First time. I know. I should have exaggerated just for your amusement. I'll be your clown. Your monkey on a stick. Let's say some mean. Oh, I could show you the meanest problem I've ever made. Someone took this heat exchanger and they mounted it on its little legs, except that the thing that they mounted it to had a gap right here. It was like some rigid base. This base is made out of, it's some huge rigid base, but some jerk decided that this thing was going to be, and I can't even remember what I gotta, it's going to be a ridiculous value if I pick too large of a value right here. But let's say that right here, they've offset this thing so it was offset. Okay, I won't even bother with the length of the thing. They had an offset. Like right here was a perfect connection, right here on the back where they mounted it here. But here, they were like offset for here from 1 degree. Can you imagine why that's going to be bad? And let's say that the length of this thing is going to be 6 feet. I can picture this on board a ship. A lot of times, like a refrigerant, it could be like a refrigerant condenser in part, because they have the, they don't look like a refrigerator. Like they usually stack the equipment right on top of each other, so they be like a compressor and a motor right here underneath it. And there might even be like almost like bunk beds. might be like an accumulator down below onto the thing. This might be the condenser up above, right? So so it's just tall and it doesn't take up as much floor deck space, right? But somebody has mounted this thing on here, and they did a terrible job of making the thing. So now what they're doing is they're twisting the heat exchanger. So what kind of load is on the heat exchanger? Torsion, right? How would we figure out the loading based on this? We just did it yesterday, maybe? At least we wrote down the equation once. It's a good one to memorize. Kind of rolls off the tip of your tongue. Was it? Yes. So if we know this, we can find the torque. Isn't that evil? Yeah, a little bit. But we could also say that it's got a pressure gauge onto the top of the thing. And let's just make the pressure gauge something big, 600 psi. G, if you were to care, because we don't care about PSIA. That's thermo. The PSIA. Everybody else just reads the gauge. We're not living in a vacuum. It's kind of funny though to say that though. You're living in a vacuum. No. Let's see. Let's get the size of this thing. I want to say that this outside diameter is going to be 8 inches. Why? I don't know. I'm just trying to picture it in my head. An 8-inch diameter, and its wall thickness. Let's go 1/4 inch. Might be too much. 1/4 inch. So the next thing that we would do probably is figure out what the inside diameter is going to be. So we need to subtract out. It's always easy to think that you're going to go minus t. It's 2t. All right. You almost want to picture that yourself right here. Here's the outside diameter, and here's the inside diameter, di. So you go, oh, there's a thickness and there's a thickness, and that's why that's 2t. So that's going to be 8 minus 2 times 0.25. So that's going to be 7.5. Did I get that right? Thank goodness for small favors. There isn't anything on here. Okay, so one mean thing I did is I also said that the temperature increased of this and that it created compression because it wanted to grow, but the feet were in place. I'm not going to do that. I'm just saying it was a homework problem. It was my first time here, and it was my first semester here, and I was like, oh boy, this is a good one. Oh, I got excited about the thing, and I made it, and then I broke them a little bit. But I tried to fix them, but I broke the students just a little tiny bit by getting just a little ambitious. I got overly excited. It was because I didn't get to teach the Coast Guard Academy. We didn't have 2 classes. We had 1 class. I mean, one course we had for machine design. So they had, and they had mechanics and materials their sophomore year, and then they had the machine design their senior year, and then they had 1 semester of it. So I was like, this was everything we do in ME370 was about 3 weeks long. So I couldn't. But when I came here, I was like, yes, it needs to be 2 courses. That's what during my job interview, I'm like, that's awesome. That is awesome. That's my dream to have two classes in this. Yes, then I could do everything I wanted to do. So I got a little excited and I made a crazy ass problem. So this was a crazy ass problem. So the thing would grow because of the temperature increase, and because of that, it would create compression because it was restricted from growing. So therefore, you would think it would be tension, but it's actually because you're holding it in place. But we're not going to do that. So we don't need a cross-sectional area because we're just going to have pressure vessel stuff with the added torsion on top. But because of that, we're going to need for geometry. So I'm telling all this because we need geometry, right? This is like the kind of thing we're going into sort of a pattern. We go geometry, loads, stresses, combine the stresses. In some manner, shape, or form. In the combined might include principal stresses, or what we're going to do the von Mises thing soon. And then the next thing we're going to do is safety factor on top of that, which is coming up very, very soon. So anyway, we're going to go pi over 32, and you're going to go, I made it as a big D, so I'm going to keep it that way, fourthed minus di fourthed. Right, so that isn't necessarily something we've done before right here, but it's not out of the realm of possibility. And by the way, I don't think this will happen on an exam, but one of the common mistakes is to fourth the outside of this, to go d minus di, and then that put it up to the fourth. That is not this. You will not get the same result, right? Just make sure you. I've done it before too myself, so it's not. I'm not casting aspersions. Oh boy, I really, really like that phrase. Aspersions. Maybe that could be a good band name. Maybe. No, probably not. I've settled there are no good band names.
We're all taken.
They're all taken. Van Halen was the only good band name. Because there is a band named Hootie and the Blowfish. And that name's taken. I probably got this wrong because I was talking while I was doing it. So you should check it too, because that's probably wrong. That seems like a really large number. But of course, I might have picked this ridiculously thick. I don't know. I can't, off the top of my head. But while we're doing geometry, one of the things we should check, what is this, thick or thin? Be nice to pick thin. Would be nice. A lot easier. On an exam, I want to see you check, but it's probably got to be thin. Save some time. All right. So yeah, so let's go. Let's the R. It doesn't matter which R. So we're gonna go 4 inches. So the thickness over R is going to be 0.25 divided by, let's just call it 4. And so actually that should be thin, right? It sounds thin. Yes, sure. 0.0625, which is less than 0.1, therefore thin. Thin, it's wafer thin. Anybody know that? Anybody? You know that? It's wafer thin. Tell everybody, Tori, what is that from? What is that from?
Oh my gosh, wait. It's okay. My dad says it all the time. I can't remember what
It's his Monty Python. His,
yeah.
his
I knew it was
is it the meaning of life? Yeah.
Yeah.
The meaning is it the meaning of life?
I think so.
Yeah, Monty Python, the meaning of life. I don't recommend playing that in front of the public. No. The guy eats too much, like and is getting large, and he gives him a thin, and he explodes graphically. It's wafer thin. Would you like a mint? It's wafer thin. All right, let's get back to this. All right, so we got thin. Any more geometry I want to do? No, okay. So let me go through, now we go to the stresses. All right, stress, we'll stress you out. Stress. The types of stress, we have torsion. Oh no, we go loads. Teddy. That's what that was what I known for 18 years, was Teddy. And then I tried to get rid of the name. And the girl I was dating at the time, this girl I used to know, still do. Saw her this morning. Go. Calls up the phones at Mercer Marine Academy. I've been there for a while. I think it was my senior year, and she accidentally says, "I want to speak to Teddy Deal." And the freshman comes up to my, "Sir, there's a young lady asking for a Teddy." Get down on the phone. I'm like, "What are you doing?" I'm sorry. You'll always be Teddy to me. All right. That's so sweet. Yeah. I'm gonna get my own damn phone. I was doing something. Yes. Okay. We need to find the torque from this. We need the J. Oh, we got the J. Oh, we need the G. We need a G. We got the L. Okay. So we need to look up. This is probably steel. So look up the thing for, let's see, where would we find it? Are you familiar enough with the book? That's a great question. For those listening at home, are you familiar with the book? Do you know enough about your book to know where you would find G if you had to? This is what you're, I'm testing. How familiar are you with this book? Could you find it? Tori can't because she didn't have a book with her. Oh, yeah, no. Just going to judge you from afar, that's all. All right, so if you had to find it, it would be in, well, it wouldn't be here. I don't think, I think, no, they did. Oh, how nice of them. They gave you the modulus of rigidity. And because Dr. Deal only cares about two things when it comes to materials, and they are steel and aluminum. So this is steel, although this could be made out of, because a lot of times you don't want corrosion, so you might make it out of stainless steel. Do they have stainless in here? Yeah, they do have. They have one stainless steel in there, and that's not the stainless steel I would pick. 316 is the only stainless as far as I'm concerned. There's a lot of others, but that's the only one I care about. Or it might be made out of brass or bronze or nickel. What am I? Oh man, I can't even remember. Nickel. Now I can't remember the. Okay, no, there's a great material that's saltwater. It's a nickel alloy, but it's nickel copper. Copper nickel, that's the way. Copper nickel is a great saltwater. It's expensive, but it's good. Works well.
Would
So
this be in the same place in the edition?
yes. Yeah, the A5. But anyway, we need the modulus of rigidity, not something we normally know. So that would be 11.5. That's what we need for that. 11.5 million PSI. Million. It's getting weirder.
When would you use the GPA?
That would be gigapascals would be an SI, right? And anytime in metric, aka metric. All right, so we wrote that it's a short attention span, can barely remember what that is. MPSI? Sure. So we want to find the torque. Let's see, can I do that in my head? Probably not. I think it's going to be, torque is going to be theta jg over L. Sounds right. But the theta needs to be turned from degrees into radians, right? So we're going to go 1 degree times pi radians over 180 degrees. And the J, I'm going to trust that I got it right, but I'm feeling trust issues right there. So the G is going to be 11.5 E6 divided by, now we have 6 feet, but that needs to be times 12 to get into inches. And I'm already thinking this torque is going to be a ridiculous amount. Like one degree is really going to be something spectacularly large. And while I enjoy that, it's going to be like a crazy Mohr circle where you're going to have this for the shear. So you have pi divided by 180 and multiply by 91.49. And it's interesting that the J is going to make the torque, but of course that actually kind of makes sense. Going to make it larger. And then 11.5 E6 times, and I think I made a mistake in picking these values because of this torsion. Are you ready? 8.26. Here, what you need to know. E to the E9. I must have screwed something up along the way. There's got to be something wrong here. Do not misalign something by 1 degree. This is what we're to learn here. You really, really crank the wrench down hard on this frame to get this thing to twist 1 degree. It turned out that's a lot, because that's going to be a stupid amount of stress. Anybody checking these numbers for me?
I didn't get that, but I also couldn't put it in the calculator.
Well, there you go. I was talking the whole time.
I got 255,045.
See, that doesn't sound as bad.
Morgan did that too. Okay, I'll do this.
Okay, so we're in agreement. I'm wrong. I don't mind. I don't mind being wrong. Okay, looks good. Yep. Thank you. Whew. Still going to be a lot of stress, I think, but we'll see. All right. I don't think we have any other loads, so 255,045. Yay! Thank you for helping me out there. We almost had a catastrophe. This thing almost just went, exploded to the moon. So stress. Let's go this one for TR over J. And we just, nobody asked us whether it was on the inside surface or on the outside surface. Let's say it's on the outside surface because, I don't know, just why not? So 255,045, and we decided it was, so we're going to go 4 for our R, and then 91.49. So 91.49 divided by 4, boom. Yeah, it's not so bad, okay. 11, I'll go KSI, 11.15 KSI. Whew, I was nervous there for a while. We were going to be like in the millions, and I don't know. It was going to be terrible, but we survived. You saved me. All right, so there was the shear through the torsion. Now we're going to go through longitudinal. Almost kind of makes more sense to go through sometimes. I guess it doesn't really matter. We go longitudinal, and it's going to be the pressure times the inside diameter divided by 4 times the thickness. Let's look it up. Don't really trust my recollection, but it's also an opportunity to point out the pitfall, right? Okay, so here is the one that I just wrote down. Pi di over 4t. Here's the pitfall, though. People often will go to this equation right there. Don't go to that equation. That equation is on the inside surface. The one that says max. Let's see. Let's look closer at him. That one right there. That's the maximum, but that maximum happens to be on the inside. The one to go to is right above. It's the average. It's thin-walled, so we really care about the average. It's kind of silly to even write this equation in here because you're already making an assumption. But we found in our homework, hopefully, that was actually a pretty good assumption. But right in here, here is where the actual one that you want to use for the outside surface is going to be. And it gets hidden because it's like right here. It's got that stuff in between. This is the, you can almost, just think of it as this is equal to this, and ignore this stuff in between. So that's the equation to use, not this one. This is sort of a distraction. It is, in fact, correct that the maximum, which is on the inside surface, which can be confirmed by looking up at this right here, you can see here's the hoop is the largest on the inside right here of there. We're concerned with the average when it comes to using the thin-walled hoop. Let's see. Okay, so here is the we have 600 psi G. Yep, 600. And the inside diameter we established as being 7.5 inches, and then the thickness is 0.25. So we get 600 times 7.5 divided by 4. Oh, and divided by 0.25. Well, that's going to be the same, right? We get 4,500 psi, or 4.5 KSI. And you could, if you really want to be cool, I don't know if that makes you cool, you just multiply that by 2. Because you notice that that's divided by 4, that's divided by 2. So it's just, the hoop is twice the longitudinal. If you're dealing with the outside, save yourself a fraction of a second. No, that's a little bit. Maybe. So now if I'm going to try to combine problems together, of course, it's not fair about the knowledge, except now it is. Now it's fair, because I told you about it, but it wasn't necessarily fair to, would you realize how to get the torque from this up above? But now you do. Now you would, right? Yeah. Gotta try to do more problems like that. I don't know how many I can. Where you combine like deflection with stress. You can get stress from deflection. So here you go. So I'm going to go and find my principal stresses real quick. This is as additional thing to try to do, right? Because this is tension, and this is tension. Of course, that's shear. So I would probably ask you to draw me, and I might need to designate a stress element somewhere, like just for the sake of designating right there, where that's X, and maybe that's Y, and that's Z, or something like that right there. So just to designate so we could, for the sake of getting a coordinate axis on there. But it doesn't actually matter on here because it's going to be any stress element that you took anywhere along this whole thing would have these stresses on it, right? There's not really any directionality except for the fact that this is going to be along the axial, right? So I'm going to make an X and Y right there. And so this is going to be 4.5. And then this is going to be 9. And then this, okay, so that's actually an interesting thing. I'm not going to ask this, but it's sort of like an interesting thing. Which way would this go? Okay, so the act of closing that bolt and tightening that bolt down kind of, and I'm just going to draw it on here. It really should be a free body diagram to put this torque in there because they're equal and opposite onto the thing. But it kind of is a torque kind of to over onto this end going in that direction. I just put it lightly into there, right? So it would be kind of a going down across that face. You buy that? And as we found, we got 11.15. So doing a rough one, I don't need to go crazy onto here. I could go like to there, and it's actually up higher above these. This is the face that has, he's the smaller of the two right here, of those spots. But it's going to actually be taller up here. So you're going to have something like right up there, and then if I'm just eyeballing it, something down over here. So you'd be like, right here's the center, right here's the R. It's probably going to be wrong. I'm probably going to, I just eyeballed it. I'll fake it. Not crazy bad, not crazy good. So that's interesting that it crosses over, at least from what I did from eyeballing it. We don't know for sure if it crossed over or not. A lot of times, if they're both tension, it might have clicked right into there. So we have to be careful with our Mohr circle because this one is really close to the edge. We can quickly find C is going to be 9 plus 4.5. 6.75. The radius, all right, so that's going to be R, and I'm just going to look for this leg, which is going to be 6.75 minus 4.5. And this height, this leg right here, the vertical leg, is going to be 11.15 squared. So 6.75, 4.5 minus square root 11.15 square root plus square root it, and go 11.37. But that's not that much. I guess, okay, I guess it's pretty tall. And then so sigma A, I'm not committing. When I do the A and the B, it's like I'm non-committal whether which principal stress this is. But truth be told, it's probably going to be principal stress 1. 6.750 plus 11.37. 18.12 KSI. Sigma B, C minus R. Okay, yeah, okay, so it is going to be a negative number, so it is crossing over there. I should have recognized that before, but what are you going to do, right? You can't be. Perfection's unobtainable. Did I get that wrong? Oh, no, I got that right. Okay. So that's going to be a negative 4.62 if I did it right. KSI. So in this circumstance where you're crossing over here, you're going to have the most ridiculous looking other two. You're going to have right there. That's a Moore circle. Can you see an itty bitty Moore circle right there? Because you're going to have this guy is going to be equal to sigma 3. This is going to be equal to sigma 1. Sigma 2 is going to be equal to 0. So you could try your very best. I could try my very best to try to get, ooh, that's actually going to be pretty good right there. There's that other Moore circle. It's kind of a little ridiculous. But this guy right here is now also going to be tau abs max. So when you have the condition where a Moore circle crosses and straddles the vertical axis, then the radius for the primary Moore circle that you had is actually going to be the abs max. And you could test that out yourself because you're just going to subtract this one versus that one and divide it by 2, and you're going to get the same radius onto the thing. So if you're going to conclude this long and involved process, you would say 18.12 KSI, and you would include that it's tension. You would say sigma 2 is equal to 0, and sigma 3 was equal to 4.62. Could put a 0 in there if you want. KSI, but you would call it compression, and you would not put a negative sign in there. Don't go negative in a compression. Double negative, and that ain't no good. Just thought of that. I gotta say that all the time for now. That ain't no good. Tau abs max is 11.37 KSI. And that's neither tension or compression, I should try to remind you. Because tension and compression is only about normal stress. There's no... We could assign a sign if we wanted to for shear, but it doesn't really matter. Because a lot of times that's just, just all about which way that you cut the thing. You're looking at that side, you're looking at that side. It only really comes up when you're trying to combine with transverse stress.
Can you show the stress again? On the other page.
Okay. Well, just speak that up a little bit.
Yeah.
Okay. Because of that, because that thing's weird. Where's he? That guy right there. I don't like it. I don't like you. It took me forever to find out. You had to get like a little tiny program thing to get rid of that thing. Some OCR thing. I don't even know what that is. No, that's not. It wasn't OCR. It was OC something. Don't matter. Taking requests. 2:39 p.m. on a Friday. What a dedicated group of people you are to do this on your Friday afternoon. Am I going to stick around for the ASME?
If you don't want to come, it's fine.
I am going to. The first one. You should all go. Become members of ASME and ASA. I know the ASA, they get all the love, man. Why people are all about the ASA and they just won't, they don't want to spread themselves too thin and being part of member of ASME. I don't know. We're gonna do the Pratt Whitney tour. One of my former students was working at Pratt Whitney, just contacted me. I forgot to send it to you. Nathaniel Hostetter. Anybody remember Nathaniel? Okay, he's been gone a couple of years. You do? Did you remember Nathaniel? No. Okay. Anyway, works at Pratt Whitney. I said, I want to do a tour. He goes, yes, let's do it. So we're going to have tours. It's going to be great. It's going to be awesome. You're going to be life-changing. You get a good job at Pratt.
There are a couple others that work at Pratt, yeah.
Okay, well, we'll get,
Klein.
yeah, yeah. All right, taking requests. Saying more Milli Vanilli songs. Trying to remember someone.
Can I see the second page again?
Okay, sure. Blame it on the rain.
How do you decide which one is up and which one's down? Does it really matter?
Say it again.
So you know how you have the 4.0 up 11.5 and the 9 is down.
Oh, I might have made a mistake too. Let me double check that I might have gone wrong.
Does it really matter?
It doesn't really matter. All right, so whether this one was up or this one was down, is that what you're talking about?
Yeah.
Okay, so I got it right, but probably on accident. This is the, that's the convention, right? That's clockwise is up the top, counterclockwise is down at the bottom, and you can look in the book for this too, to confirm that, sorry, I'm just amusing myself with this book. It's a very silly man. This is a very silly man. There you go. I'm gonna play Milli Vanilli. Right here. Then it says clockwise. You can barely read it. Let's see here. Where it says clockwise, and then it says counterclockwise. Oh, they played this one first? Come on, this is terrible. We gotta go blame it on the rain. I'm sorry. Girl, you know it's true. Ooh, ooh, ooh. You got a better request. I think we're gonna play some more Milli Vanilli. How you get punished for not like requesting a problem? We haven't done door handle. We haven't done 3D shaft. Shit. We're gonna get moving. They're not really singing this. It's like somebody else's voice. They completely, and then they tried to make a comeback where they actually started to sing, and it was just terrible. It was one of the coolest things. The coolest. It was fun. It was fun. A band that I hated so much to be so thoroughly disgraced was just awesome. It was just awesome. And especially my roommate, Chris, my short-time roommate. Not as bad as Brian Hunt. He was after Chris May. Chris and I just didn't get along, and we decided amicably. I just actually just moved across the hall. Brian Hunt, it was a year after, he was a year older, my sophomore year. Because Andy was mad at me. My freshman year, I talked about Andy Busk all the time. Sophomore year, we didn't room together because he was mad at me. I went out to sea, and I got in a cab in Alexandria, Egypt. And apparently, this is a very entrepreneurial cab driver. He would pick up students. He would find out a ship came in and they had a cadet on board from the Merchant Marine Academy, and he would say, "Hey, Kings Point, come into my cab." And there was like a date book that he had in there with entries from people I knew all across the world in Alexandria. And I'm taking this cab ride, and I'm reading through, and Andy's girlfriend writes something in here, and I really hated her. I really did. So I wrote something that was not gentlemanly. And then, like, apparently that set off a chain reaction that I didn't know about, and everybody said something bad about her in this little journal thing. And I get back to school, and Andy's waiting for me. Took a while for him to get over that. We did. We became roommates again junior year. But anyway, you didn't need to know that.
Did you break up with her?
Yeah, they absolutely did. Yeah, absolutely. No, not because of that, but yeah.
So did you do him a favor?
Oh yeah. That was dodge that bullet. That was a bullet and a half. Anyway, we won't go down that road any further because it was not my finest moment. No, not my finest moment. It was funny though. Door handle, I guess. Let's pick a door handle. You're not playing nice. 15 minutes. We could do a 15-minute door handle. Here's the example door handle, by the way. Always left to your imagination the classic door handle problem. But let's make a more complicated door handle. But the free body diagram is not how I want you to do free body diagrams. So do not mimic their free body diagrams. I do not condone this method of free body diagrams. I think it's hard to learn this. And I think it takes away from the visualization that you need to do.
It's extremely painful.
It's not great, but it's just, I don't know. I just don't find it to be the way that would stick with you for a lifetime of engineering were you to come back and relearn this type of thing. Here's also another door handle right here. I think sometimes it's a little too simple. But you could make them complicated because they do have different choices as to what forces to put onto the end. Let's see. Of course, they have the classic door handle, and then there was I got really excited in one of the videos that's up. You could see how excited I was when I turned a page one day and found another door handle in here. Right there. Oh yeah, these door handles were fresh door handles. Let's do this one, because I've never done this one in a class. In a review session, this will be the first one. All right. So let's see if we can get that one done in 15 minutes. We might go into overtime because I wasted Milli Vanilli time. Now you know about them. You can, if you're ever on Jeopardy and there's a Jeopardy question about Milli Vanilli, you're going to be gold. You're going to know. My kids used to watch me watch Jeopardy, and I would call out the answers, like every one of them, and they thought I was a genius. Years and years ago, my kids thought I was a genius. They don't think that anymore. Actually, I think my sister. Ooh, that was a Freudian. I think my daughter is coming around. She asks me questions, advice. I'm like, really? You care what I think? It's pretty amazing. Keep wondering, has anybody met my daughter? Anybody know her? No? Do yourself a favor. Meet my daughter sometime. I want her to come to class and teach a class. Just some whatever random topic she wants to talk about. I think it would be life-changing for you. All right, so let's see. This one's 60, and this is 75. And let's see, these distances are 6 inches and 5 inches. I didn't leave myself a whole lot of room here. This is 5.5 somehow. 5.5. This is not dimensioned very well by me. Of course, they didn't do a great job either, because check out what they had to do that thing underneath. That wasn't their finest moment either. And I guess this is B, and this is D. I don't know if we need to know that. And A. And if we're going to try to actually use the thing, they say lots of words here in the Z direction. Let's see. Consider this to be the X direction. And that's the Z. And this is the Y. Kind of squeeze them in there. Determine the precise location of the critical stress element at the section at A. Okay, so in this case, they're not talking about a particular element. They're talking about the critical one. So it could be anywhere around this section. So because of that, let's go ahead and pick the one that's on top. Just call it that. All right, so we're trying to find a one that's, here's our X and our Y, the one that's going to be on top. So the first thing, we get to get rid of some geometry, and find the area pi over 4d squared, the I, pi over 64d squared, and the j, which is going to be 2 times I. Oops. All right, I can actually probably move this over to the side. Girl, you know it's true. Ooh, ooh, ooh. Hate that's in my head now. So let's see, it's 0.75 inches. So square it, multiply it by pi. Was that right? Okay. Divided by 4. 0.4418, call it. We get 0.75, raise it to the 4th. Is that true? Well, that's weird. We'll try it again, 0.754. Yeah, it's the right number, okay. It's just weird, it looks like I was trying it to be pi when I did that. 64 divided. All right, so we're going to go, I guess I'll write it out this way. 1553, yes, inches fourthed, multiply by 2, 0.03106 inches fourthed. Cool. Now we're going to go loads, and I guess I'm going to go on my FBD. Let's go XY first because that's in the alphabet that way. Make this thing look like that. And okay, we're going to have our 60. We're going to see from the side. We're going to see our 75 coming up. Oh, but
I get inches 4.
I meant fourth. Sorry. Thank you. I put this in that way. I just brain not worky. This thing is in front of this guy, so I'm going to put him right over there at 300. Just didn't leave enough room. And you can't see the 200. Okay, so we're good right there. We're going to have a reaction. This is going to be down, so this is going to be up. So we're going to go RY, RX, and then our moment. This is pretty easy. This is going to cause it to go clockwise. So I need that way counterclockwise as a reaction about the z-axis. I can save myself some time in this situation because I said that I'm only going to look at the top right here. I don't have to look at the top frame, the XZ direction. I can recognize that, save myself some free body diagram time, because it would, looking at the thing, it would look like this right here, right? I said I could save myself some time, but here I go doing it. But it doesn't hurt to, like think your way through the piece. And okay, excuse me, you see this one is 60. So I kind of prefer, I kind of would prefer to have asked the one on the side, because this is, actually that's not so bad, because this is going counterclockwise and this is going counterclockwise. Is that true? Yeah, about here, yep. So you're going to have a reaction, the MY reaction is going to be going that way. Here's our RZ, here's our RX, right there. So, but like I said, you don't actually need this one if you followed what had been done. And so in this exam, I'm not doing that worst element thing, because I still want you to demonstrate you can figure out which combine and which don't combine in terms of the types of stresses, right? So that's something I'm going to stress. Sorry, I should stop that. I'm going to start doing more puns, maybe. Maybe if I try more puns, I will do less puns, I think. So anyway, if you do the sum of the moments about the z-axis right here, we get this is a simple problem. So I might ask something that was a little bit more complicated, so just so I could see that you could do it. Not because I'm trying to be cruel, but because I'm trying to trying to be kind. No, it's not true. I'm trying to to measure. All right, so it's going to be 75 or 300 minus 75, 225, right? And that's going clockwise. So I'm going to write that 225. And this distance right here was 5.5. If you look up at the, and you can actually see that up in there, 5.5. So MZ is going to be 5.5 and 225 times. So we're going to get 1,238 inch-pounds. I'm going to ignore, because, again, this does not create a stress at the top, which I decided to do instead of doing the maximum. And then the last one, the FBD, that we'd be looking at, we've got to look at it from the front, so that's going to be in the YZ plane, and it's going to look like this right here. And we're going to have a 75 right here. We could see the 300 right here, and we're going to have the 200 right there. In terms of reactions, we will have an upwards reaction to the 300, and that's going to be RY. We'd also have a reaction coming this way, which would be the RZ. And then this is the only guy that creates a moment, because this is 300 is going through the center, 200 is going through the center, so 75 is going clockwise. So we will go counterclockwise, and that's going to be MX. Oops, in the way. And MX is actually going to be equal to the torque. So sum of the moments, and he just said sum of the moments and then started to write an F. And he's talking about himself in the third person again. What's a strange man? We go MX minus our 75 pounds, and that distance for the moment arm, you can't, it's up above, up there, but it's going to be 5 inches. It's to right to there. So MX is equal to 75 times 5, which I feel like I could do in my head. No, I couldn't. Inch pounds. And by the way, that's equal to the torque. I could also, by inspection, look here and work through that. Just, we could say that RZ was equal to 200 pounds. We could have said that RX was going to be equal to 60 pounds. We could have said that RY was going to be, well, it's the difference between the 75 and the 300, so that's going to be the 225 pounds. We could have written out some of the forces to do that, but it seems kind of silly sometimes to do that. So those are the loads, and then we go to stresses. And so we go axial first. It's a good place to start. And that axial is going to be the 60 pounds, right? Or you could see that it was right here in the x direction. Probably not going to be a lot. 0.4418 is the area. It's only 135.8 psi. Not a lot. It's tension though. Bending. And this is at top. I don't know. Is going to be MC over I, And so the moment that we cared about is 1,238. That creates a bending moment. And since it's on the top, we note, by the way, it's going to be right here. And we can tell by this moment, we don't have to even look at the stump. We could tell from here that's going to create tension right here at the top. This is 0.375 because it's 75 divided by 2, so the C is half of that. And then we had 0.01553. So 1238. 0.375 times 0.01553 divided. So we end up with 29.89 KSI, and this is in tension. So if you want to have like the total stress in the x direction here, it's going to be the axial plus the bending. And I will say that there's a good, strong chance that I would probably, whatever I ask you to write, they're not going to be the same direction. What? Need to move up? Yeah, thank you. Not because I'm trying to be a jerk, but because I want you to demonstrate that you know which one is going to cause which thing. I try. I'm not guaranteeing that, but. So anyway, you put those two together, and it does actually make it all the way up to 30.3. But I'm going to try to make the numbers so that, you know, because there's always little silly little math mistakes, and never everybody's going to make the same thing. But I try to make them substantially so we could tell the difference. And then the last one we're going to have for, no, not the last one, not for this. We do want to be able to do the transverse. So TR over J, we're going to have the, where did I go? 375, yeah, times 0.375 divided by 0.03106, so 375, 0.375 times 0.03106 divided. So that's only going to be like a 4.528 KSI. And then the last one we want to do is transverse, which we know is going to be 4/3. I like to go V, but it could be, you could put an F if you want, I don't care. So 4/3, and now here's the important thing, and I haven't given enough room right in there, is what force causes transverse shear at that top element?
200.
I heard a 200. Anybody want to agree with or disagree? You're going to agree? That's good because that's true. That's good news. So you divide by 0.4418. And by the way, the next question should be, how did you know that? If you don't know it.
If I don't know it,
I mean, you explain how you know it then.
well, I look at the face that we're looking at, and I think of a perpendicular force going across the plane as a shear force.
That's a good way to look at it.
Identified the 200 that was going across the shear. Was the shear across the plane?
I think I understood what you said.
Yeah. Easy right from
Some of those words sounded right up to a point, then I was like, I'm confused. All right, so didn't leave myself a lot of room. Do I want another piece of paper? I have a lot of paper. See, that we should demonstrate, like, you know, when sometimes people want one pad of engineering paper to last an entire 4 years. That's what I think some people are trying to do. So I suspect. Trying to squeeze everything in there. And thereby increase the difficulty of solving the problems. Just buy another pad of paper. Spread it out. But anyway, so now we want to do the most important thing here is to combine. Well, I already kind of did that right here. I talked about that. And so that's going to be the 30.03 KSI. And that was going down in line with the X. Okay, we're good. Here's a question. Is there any stress right here? No. That is correct. And any normal stress? No. No normal stress there. You put normal stress there, I take off points. What circumstances would there be stress perhaps there? What if this thing was hollow and we decided to put hoop stress? Yeah, if we decided to, we made it hollow and put some pressure on there, we would get some tension. All right? That's the only circumstances under which you would have stress here and you would have normal stresses on both faces. That's the only one that we've encountered. We could also be a rotating ring or a press fit or that type of thing where, you know, we'd come up with a scenario where we had that. But I've had so many students that put the bending here and the axial there that I want to just try to say explicitly out loud. I don't know if we had to be redundant like that, explicitly out loud. I just want to say, for sure, do not put that there. It shows a lack of understanding. And that does, I must grade it accordingly and say, hold on, wait, alert, 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 alert. We must, you know, sometimes in homework, there's points, I take a little point off because that's get your attention point, right? Just, I'm going to get your attention so you'll remember the thing. But that's like, there on an exam, it's like we're measuring your mastery and you have not mastered the thing. You have a big hole in your perception of how things work in this world, and we need to be measured accordingly. All right, so the next part of it is the torsion and the trans. Not nearly as important, but still part of the visualization thing, part of picking it out. And so when it came to the torque, let's just say, should that go up or down across this face right here? And let's take a look back up over here at the original thing, which is not, this is not a bad approach to doing this. First off, recall what caused the torque? What load? Was this one? The 75 was the guy that caused the torque.
So it should go up.
So yes. So on our face right here, that should be an upwards type of thing, right? Because it's going across, like you picture looking down at this piece, which is right here. So that would be a shear going in that direction. And then, do you have that, Kyochi, do you have that organized?
Yeah.
Okay, cool. All right. I was looking at your face. I was like,
My drawing's not as good as yours.
no, I'm sorry. Well, hey, I'm not being facetious. I don't know if that's not the right word. I'm not being condescending. I'm like, I honestly trying to get better at drawing and sketching. Honestly, it will help you. It will. Sometimes just take some time or like just little things and just practice. Do it for other things and just, it's also an enjoyable thing to do, just draw things. But aside from that. All right, so what about the trans? You kind of already said it though. Yeah, well, which direction does it go? Up or down on his face? Up, down, up, down, up, down. It's going up, right? Everybody else okay with the up? And it's because of that 200 pounds. That's the one that was causing it. And so that's going, boom, it's going across the face that way. So that too would go up. Therefore, they add together. That's the important thing to do. And just, want to make sure that we all master that. That's what we're here for, right? That's the review session, is to try to, put it all together, but also to recognize what we don't know and what maybe want to try a problem where we have a solution without looking at the thing and measure these things in yourself, right? So what we had there for the tau and the torque plus the trans, The torque is going to go, where'd the torque? Where'd you go? It's 4, I guess I'll do it this way, 4.528, and the trans is 0.6036. And add them together, and you get 5.131 KSI. So there you go, 5.131 KSI. And just quickly, to be clear, if you were asked, and I'm not going to ask it 4 times for the principal stresses, but if you were to ask for the principal stress in this circumstance, first you would write it up like this, but then you would put this on here. In this circumstance, which we could call uniaxial stress, that's the way, like this is biaxial stress. This is uniaxial stress. It sounds like it's on a unicycle, but it's not. But it'd be funny if it was. You would have on this face right here, you're going, there's 0 normal stress, but you're going clockwise. So what you would find onto that is you would put that to like right there, right? Nothing in the normal, so it ends up on this. So I don't think we've done many of these. This is probably the most common, and it's kind of ironic we haven't done many of them. This is the most common scenario is this stress right here. Like it only happens with the other ones when we have a pressure vessel, right? Basically, so if it's not a pressure vessel, chances are it's uniaxial stress, and so we have it's the same level here. But now we're going to, and notably, by the way, this was clockwise. That's why it's up on the positive, right? Somewhere over here, right? So we'd go like somewhere over there, and I didn't do a great job of making this symmetric, but we're going to see that should be symmetric. Anyway, I'm going to pretend like it was bothering me. Okay, so somewhere like there. There's a, okay. Here's where the center is, right there. Okay. So this is a coordinate of 30.03, comma, I know what time it is, so I'm just going to go negative 5.131 going on that face, and then but right here we'd go that this was a 0 and a 5.131. So yeah, I got close. And in this case, by the way, this always straddles the line. Just always going to do that thing. And of course, I have an itty bitty tiny Moore circle that's happening right there because I did a lousy job of setting it up because I didn't really try that hard. So that's my excuse. Didn't try hard. Which I use the word try hard, which I think is kind of a funny thing. My kids called the other kids at school tryhards. I'm like, what's a tryhard? I said, oh, you know, the kid does all their homework and asks questions in class and things. And I'm like, why aren't you a tryhard? Why aren't you a tryhard? So C is going to be equal to, well, it's just going to be equal to 1/2 of this because there's nothing, you know, I could write plus 0, and I just did. But you could find that you're going to get 15.01 KSI. And then R is fairly easy because that's just going to be this. So it's good that we didn't do too many of them because a lot of times people just mistakenly see me doing this over and over again and they don't realize that this is what we get for one of the legs is actually equal to the center, right? Because of this set of circumstances, this distance right here is equal to the length of the center. We're okay with that? You can see why some people would get confused, though, if they see a lot of these problems and they didn't realize that to get the leg, you need to look at the leg. And then this is 5.131 squared. So 1,000 squared, and 5.131131 squared plus square root, and we get 15.87, not a lot, not very much bigger than that, KSI. So we have A, C plus R, which is going to be 15.01 plus 15.87 did I do that wrong? I did that wrong. 15.01 15.87 plus, so we get 30.88. Once again, not just because the way things worked out, because the relative values between here and here, it doesn't change this one. But this is also equal to sigma 1. Sigma 2 is going to be equal to 0. I should have done sigma b first here. But it's going to be C minus R. And this is going to be a very small number because we're really close to the thing right there. So you're going to have 15.01 minus 15.87. So you're going to get a negative. And right here, I should have got more sig figs because I'm not going to be left with many here. And minus 0.86. I'll call it 0, but I don't really know because I got rid of some sig figs along the way. Dropped some, and this is a small value. But anyway, you would find that, to summarize, sigma 1 was 30.9 KSI tension. Sigma 2 is equal to 0. Sigma 3 is 0.860 KSI compression, and tau abs max, because it's doing the straddling thing, is going to be equal to R, or 15.9 KSI. And I lied, it took me like a half hour, not 15 minutes. But then I went ahead and did the extra stuff. I didn't have to do it. I didn't have to do the more circle part of it. I didn't do a 3D shaft, but I don't have time to do it. But so I encourage you to look through. There's plenty of examples of doing one, and like chances are it'll be a 2D shaft because 3D shaft takes too long. But if I were to do a 3D shaft, what I would generally do is one of the planes I would complete the shear moment diagram for you. So then you could just run from one plane of it, and but anyway, I am available if you have questions via the Collaborate. We can make an appointment together if you're stuck on something. And think about coming to ASM. And think about looking up Milli Vanilli and becoming a huge fan. I'm sure they're playing clubs somewhere near you. I will not be doing that, ever.